Hi everyone, my name is Harshil and I'm an MS in Data Science student at Columbia. Today I'm going to be talking about a project that I did in connection to the Applied Deep Learning course. The goal of this project is detecting cancer metastasis on gigapixel pathology images. This problem statement is in connection to the CAMELYON data challenge, which is widely popular in the field of breast cancer research. The goal of the challenge is to develop a model to automate the process of detection of metastasis on whole slide images of lymph node sections, and that can greatly assist pathologists in their examination of whole slide images uh, so as to reduce the misdiagnosis rate and increase the sensitivity of the diagnosis. And if you think about this problem, it is essentially, if you think about building this model, it is essentially a binary classifier that needs to be built to predict whether or not a slide contains tumor. But in practice, it is more meaningful to extract patches from an entire whole slide image, make predictions on each of those patches, and generate a heat map, which can then be overlaid on top of the actual whole slide image to highlight the regions of tumor. In this, for the purpose of this project, I came across a research paper which works on a very similar task, and the idea, and then I found it very useful to extract tips from the research paper on what worked for them in the implementation of this project, and some of them are shown over here. So what they did was they utilized a transfer learning based method using the Inception V3 architecture. They used patch sizes of 299 cross 299 with strides of 128. For each input, they predicted the label of the central 128 cross 128 region. Surrounding region in the patch acts as the context. They label patches as tumor if at least one pixel in the central region has tumor. They experiment with multi-scale approaches that utilize patches at multiple magnifications centered on the same region. Using 4 magnification levels shows no benefit, and they work with 2 levels instead. They rotate each input patch for data augmentation by 4 multiples of 90 degrees. They flip left right, and in this process, they generate 8 times an augmentation. This can be done because pathology slides have no canonical orientations. For further augmentation, they also perturb brightness, saturation, and hue with certain max deltas. For the data selection and image extraction, for my project, I've worked with 3 slides, and the third one is set aside for testing and heat map generation. Training data is extracted from the first 2 slides, with patches of dimension 299 cross 299 extracted with a stride of 128, as in the paper. Further, labels are assigned based on the central 128 cross 128 region of each patch, and a label of 1 is assigned if at least a pixel of tumor is present in that central window. Further, I work with level 4 of each of the slides, which is roughly of the order of 5000 cross 5000 pixels. I also experimented with levels 3 and 5, but ended up with either memory or data scarcity issues. Here's a snapshot of the slides that I used for this project. The slide to the left, which is 84, is the one used for testing or heat map generation, and the slides on the right are the ones for which patches are extracted for training. Right, and data selection. For data selection and image extraction, patches are selected if and only if they contain at least 20% of tissue. And this seems like a good threshold because below it, I end up with a very high number of negative samples, and above it, I end up with very low number of positive samples. And given it's an imbalanced classification problem, I want to ensure that I get as many positive samples as possible for the classifier to learn from them. And for 2 slides, namely 91 and 75, I was able to, for the training ones, I was able to extract 620 patches with around 80 positive examples. And from the testing slide, I was able to extract 470 patches with about 30 positive samples. And for the data augmentation, in order, first of all, to deal with the class imbalance, I oversample from both the positive and negative class members to get an equal number of data points, basically 1500 per class. So hence I have now 3000 data points for training. And I do a 90% 10% split for training and validation from this. So I end up at 2700 for training and 300 for testing for validation. For training, I set up data generators for rescaling and horizontal flipping. Horizontal flipping is the only data augmentation I use. And for validation data generator, I only do rescaling. A batch size of 32 is set for both the data generators. And for the test slide, I normalize the images as was done for the validation split. Now I'll switch briefly to the code that I used in the process of building this model. And as you can see over here, I start with viewing slides at level 4. These are the slides at level 4 zoom, this one being the one for test. And now the next step is to determine the number of strides to take for each slide across the width and the height of the image. And once I've determined that, I can then start moving a sliding window over each of the slides. First, I start with the training slides, which is the first two slides, and I'm able to extract roughly 620 patches, of which roughly 80 are positive. And here I've visualized the positive and negative member. Over here, I've overlaid the mask of the patch on top of the patch itself to show you in red the regions which contain tumor. For the testing set, again the same process is repeated from the third slide, and I'm able to extract 470 patches, meaningful patches, which contain at least 20% tissue, of which 30 are positive samples. And over here, I implement the oversampling from both positive and negative class members to generate equal number of data points, that is 1500 per class, and overall 3000 data points. These are then shuffled and then split into train and val for the training and validation data generators. As you can see, the training data generator has rescaling and horizontal flipping only, while the validation data generator just has rescaling, which is just normalizing the image. And then we feed the training and validation data to the training and validation data generators respectively with a batch size set of 32. And as I mentioned in the presentation, two training strategies are attempted. One is transfer learning with Inception v3, from which I extract the base of the transfer learning of the Inception v3 model, and on top of that I add a couple of dense layers. And then I also train a simple CNN from scratch to just see how it compares in terms of performance. I define two checkpoints for both of these models, and the checkpoints look something like this. I define a model checkpoint to store the best model with the highest validation accuracy, and an early stopping callback to ensure that I stop training once my model starts overfitting. For that, I monitor validation loss and set a patience of 2. And now coming to the architecture of the transfer learning based model, we take the base of the transfer learning model, and on top of that we add a global average pooling layer, a dense layer with 256 neurons dropout, and then a dense of 1, which is just the output layer. I compile the model with binary cross entropy and an Adam optimizer with a relatively lower learning rate. I can use accuracy as a metric over here because I've artificially balanced the dataset. Coming to the training process, I set 15 epochs. I pass my training data generator and my validation data generator and the callbacks. And as you can see, the model constantly monitors the validation loss. It also saves, if there's any improvement in validation accuracy, it saves the model with this name. And as I go down, here I can see the training history plotted. And as you can see, a good sign is that the validation loss goes on decreasing, which shows that there's no sign of overfitting. Coming to the evaluation, so this is for the transfer learning based model. I want to quickly, before I get to the evaluation, I just wanted to talk about, I want to show you quickly through my basic CNN as well. So the basic CNN has a couple of convolutional layers, a couple of pairs of convolutional layers followed by max pooling layers, and then a couple of dense layers on top with a certain dropout to prevent overfitting again. This is how the architecture looks like, and again, to have an apples to apples sort of comparison, I compile with the same sort of settings with learning rate of this value with an Adam optimizer, an accuracy metric to evaluate, and a loss of binary cross entropy. And again, and over here, I train my model for 5 epochs because this model starts overfitting very quickly. So I don't train with as many epochs as was done previously. And again, I pass the same training data generator and the validation data generator with the same callbacks list, like so. And as you can see from the history callback of this model, the loss overall has a negative trend. The loss goes on decreasing, which is good, the validation loss. But the validation accuracy also overall has a positive trend, which is kind of good. But as we can see now from the model evaluation, which I will show very shortly, we can see that these are the scores for the transfer learning based model and the basic CNN. These values are reported based on default classifier probability threshold of 0.5. The basic CNN seems to be overfitting quite a bit. Further, the false positives are very high in number. This can be seen because of low precision. And from the comparison of the two models, it is clear that the transfer learning based model is much superior. It is important to further calibrate the probabilities to get the sensitivity up further. Ideally, we're looking for a really high sensitivity with very few false negatives, and at the same time, you want to minimize the false positives as well. Given the nature of the problem, false negatives are clearly more important than false positives, which is why recall becomes a priority. Here are the confusion matrices from the two models. And with it, of course, these are based on the default probability thresholds of zero point 0.5. So as you can see from the confusion matrices, we don't have too many false positives or false negatives for the transfer learning based model, and the recalls are fairly decent for both the negative and the positive class. But what you do want to do in practice is kind of minimize this number, get the number of false negatives down further. Whereas over here for the basic CNN, we can see that it has a huge number of false positives, while the false negatives is kind of low, which is why it has a high recall. But we want to also have a model which kind of doesn't predict everything as having tumor, which is why we want to minimize this number further. And in order to reduce the false positives for the basic CNN, I kind of choose a higher probability threshold, that is 0.7, which is above 0.5. Whereas for the transfer learning based model, as I have a fairly decent, precision, what I want to do is now maximize recall. What I want to do is now increase recall, maximize recall, which is why I kind of shift the probability threshold down below 0.5. And as I can see over here, I get a higher F1 score overall because of a huge increase in the recall as I decrease the probability threshold. And this of course leads to a decline in the number of false negatives. So finally, a threshold of zero point 0.4 seems to work best for the transfer learning based model, and a threshold of 0.7 seems to work best for the basic CNN. And these are some heat maps that are generated in the process. This is a binary heat map with a probability threshold of 0.4 for the transfer learning based model. And this is the ground truth. This is how this is the mask. This is the actual mask for the third slide, whereas this is what the model predicts. And as you can see, the tumor containing regions are correctly predicted, with a few surrounding regions also predicted. But as can be seen further in the probabilistic or the grayscale heat map, the actual tumor containing regions are kind of labeled darker, with the false positives, as you can see, labeled lighter, which implies that the model is lesser confident of these regions containing tumor, which is good, and the model is highly confident of the actual regions containing tumor, as they are in the ground truth. So this is the final output of the transfer learning based model. And coming to future steps that can yield further improvements in the performance, fixing overfitting with the basic CNN model, for instance, reducing the number of parameters being learned, changing dropout, and the number of neurons for hidden layers, can be the next step to kind of improve the performance of the basic CNN. Of course, getting more data for training by using more slides greater than 2 for the training patch extraction would help a great deal. And fine-tuning the transfer learning model would also help in improving its performance in terms of the overall precision and recall. And tuning probability thresholds further at a higher granular level could also help me decide which threshold might work even better compared to the ones already determined. And considering 150 cross 150 patches with central windows of 64 cross 64 and stride of 64 can yield more images per slide, as well as more coverage around the corners. And increasing the number of augmentations, for instance, with more rotations, can also probably help increase or overrepresent or kind of increase the representation of the minority class in my training data set. And yes, that is pretty much the project, and I would like to thank you for your time.